In this video, we're going to take a look at how to prepare our text mining data with TF-IDF. So first of all, TF-IDF is term frequency inverse document frequency. And when we're text mining, this is useful because it will take a look at the frequency of terms in a specific document. Remember, a document could be anything with words that we're looking at: an email, a chat message, a text message, or even voice to text in real time or near real time. So the term frequency is simply how many times does the term T appear in document D. And the frequency of terms within document is a bit of a logarithmic expression that just says, okay, for this specific term, how frequently do we see it in documents? We might want to eliminate from consideration any terms that are very infrequent, that are, words that aren't used frequently, or words that we would see in every single document, and therefore it's not a differentiator. On the other hand, if the term is somewhere between those two, maybe it's a rare term we see in a few documents, that might indicate something of value. And that's where we can apply some interesting regression after we've done this TF-IDF analysis to see what are the words that trigger a certain outcome that we're looking for. Now, TF-IDF will generate a number, and the higher the number, the more unique it is within documents. The lower the number, the less unique it is within documents. There are a couple of different approaches we can take. One is to use the Tfidftransformer. And with that, we will separately need to create a CountVectorizer and parameterize that. The other option is the Tfidfvectorizer, which does the CountVectorizer for us. So what's the difference? Well, the CountVectorizer is something that will take a look at the words and create a matrix of where it sees the words. We can either create a frequency count where it says a number that indicates whether the word, how many times it has seen the word, or we can simply do presence and absence where it's a Boolean mask where it says the word appeared here in this document one or more times or 0 times, and that would be represented by a 1 or a 0 respectively. Now, what's nice about the CountVectorizer, though, what's nice about pulling that out is we can provide it with things like stop words. So we can say, okay, don't include these words. And there are default stop words lists in several languages, including English, which we'll use. We can also limitize the data before providing it to a CountVectorizer, so we can effectively stem all the words, take them back to their stems, and also club together synonyms as one word. So that's why we would use the Tfidftransformer instead of the vectorizer, is if there are any parameters we want to pass to the CountVectorizer before doing a transformation. We see here an example constructor of a vectorizer where we're telling it a max number of features, and then we're passing in a series of words. And the transformer, very similar. As a matter of fact, I think this one's easier to show by demo, which I will do in just a moment. Now, what we'll see is that the TF-IDF analysis creates a sparse matrix. Now, consider a two-dimensional data structure that has a lot of null or empty values. You're going to waste a lot of space storing zeros or empties. And so what the sparse matrix will do for us is it says, okay, I see that there are a lot of zeros in this two-dimensional structure, so I'm going to take them out. And what I'm going to do is just give you the location where I see any non-zero data. Remember, we start counting with 0. So this would effectively be column 0, the first column, which would be our first document. And then this would be an index that represents a certain word. So that would effectively be a row, and this would effectively be a column. And then these are the TF-IDF numbers that we'll see. So you see 1.98, that indicates a word that is fairly common as opposed to like a 3.07. Or even this one here, 6.15, which indicates a much less common word. And a lot of times those are what we're going to want to investigate. Let's take a look at a sample that I put together. I went out to my own LinkedIn site and I grabbed about 8 jobs that I saw here. And what I was looking for is something that says what you will do. So sometimes you'll see like a job description here that says what you will do. And I was just grabbing these first couple of paragraphs to look for some words. Now, to make this a true good data mining exercise, we would go ahead and grab the entire document. But for our sake, I wanted to just grab a little sample. So I grabbed about 8 of those. I also went to my own profile and grabbed my about. And the idea here is that we can take a look at jobs and we can take a look at a candidate. So I start by saying, okay, this is what I'm going to import. Several imports were needed. And then corpus, which is effectively the body of data that we're going to take a look at. Now, I put each of these job descriptions into a text document, and each text document is named after the organization that is hiring. So you see I have just a few samples here. And again, for a really good exercise, we would grab the whole document, although I will say job descriptions tend to be over wordy more often than not. So we want to be careful of that as well. Nonetheless, you see here, I've created a function that will read the document and take its contents and then print them out just so we can see them. And then append the contents to this corpus, which is the body of words that we're going to be processing. So we'll go ahead and create this function. And now just to test one out, I'm going to read in kforce. And we notice that kforce is going to, when I read in the kforce file, it's simply going to output that because I told it here, read the content and then print the content. And we see the content here. And you see, sure enough, that matches up to what I have in this kforce document, experience leading and managing a team with direct and indirect reports. So there we have that. Now let's validate that it got into our corpus. So we take a look at our corpus. Notice the only significant difference here is the square brackets, and the entire unit is enclosed within single quotes to indicate that this is one item of a list, and the one item is enclosed with those single quotes. Now I'm happy with that, so I'm going to go ahead and read in 7 other job descriptions. And we see it prints them out as the function does, not a big surprise there. And now let's take a look at the corpus that results. And again, we see square bracket and single quotes and comma. And then it looks like it put this one in double quotes and then comma, this one in single quotes and then comma. So effectively, each of those job descriptions represents a different job. And if you just kind of take a look at this, you can see there are some words that you're going to see more than once. I mean, skills and ability, you'll see that several times. Manager, master, you'll see that several times. Now, next thing I want to do is read this into a CountVectorizer. Hang tight on lemma tokenizer. We'll come back to that in just a moment. Let's focus down here on the CountVectorizer. So we start with the CountVectorizer. We start by instantiating that, and then we're going to say Tfidftransform with corpus, where corpus is this collection of documents we have above. And then we're going to print out the document matrix. Let's take a look at what we get here just first time around. You'll see we have S1 through S8, which represent our different documents, or in this case, each of those different job descriptions. Now, if we take a look down towards the left, we'll see each of the words that it's looking for, and we see 267 rows, which means it picked up on 267 unique words. Now, if each of those are a feature, we're going to have quite a few features. So we need to think of a few ways that we can consolidate this. And one is by using stop words. The other is by using limitize. A couple different approaches we can take on both of those. If I want to use English stop words and not limitize, it's fairly straightforward. I just pass in this parameter, stop words equals English. Now let's try this. And remember stop words is going to take away any words that are very common. So I wouldn't be surprised if it takes away you or your. Let's take a look. But the bigger thing I want to pay attention to is the number of rows down here. So boom. Notice with stop words enabled, stop words English. Sure enough, it took away you and your because those are common words that wouldn't necessarily differentiate one job description for another. But you also notice that we went from 267 rows down to 227 rows because it eliminated about 40 common words. So now we have a better model to deal with. But what about limitizing? Let's take a deeper look at these words and see if we see similar words. For that, I'm going to go ahead and change my display max rows so that we can look at the entire count that came out from our CountVectorizer. Now we have a few that have similar stems. So analyst, analytical, analyze. That one's tricky though, because are those necessarily the same words or different? Not sure. But if we look below, we have business and businesses. Those have the same root. Collaboration and collaborative. Those have same root. Coordinates, coordinating, develop, development. So we see several areas where we can consolidate based on a common stem. We're going to find a bit of a funny scenario here if we try to both lematize and use stop words together. So let me go ahead and create this class that I glazed over before, but we'll go ahead and create it now. So note that we have a class. We have an initialization function and then a call function. In the initialization function, I'm going to instantiate English stemmer. So take English words back to their stem or back to their root. Now in the call function, I'm going to say, okay, we want to use that stemmer to stem each word in this document that we're going to receive, provided that the word is alphabetical. So go ahead and create this. Now let's run this next line. And one change you'll see here is I've added a new argument to our CountVectorizer called tokenizer. So it says, okay, I kind of expect you to be able to tokenize some words. What tokenizer are you going to use? And for that, we need to pass in a class, which is the class that we used above. So go ahead and run this one more time. And, okay, well, you see, now it's showing us just stem words, which is great. Looks good. If I scroll down a little bit, we'll see... Okay, we have several stem words, and then I have a big warning here. Well, what the warning is effectively telling me is, well, hang on a second. You've given me English stop words, but then I'm not looking at whole words. I'm looking at stems of words. So my stop words isn't going to find anything in here, or at least it will find some things, like it did find the you and the your, but it's not necessarily going to know how to deal with the stem words. So what we can do for that is we can go ahead and we'll take out this second parameter here where we're telling it to use English stop words automatically. Instead of including the stop words down there, let's include the stop words filter up here in our lemma tokenizer. So I'm going to add and T not in self stop words, and then I'm going to uncomment this line up here. Okay, so what's going on? Well, we are grabbing the English stop words. If you're curious what's in there, I just put that on the second line here and printed it out so you can see a, about, above, across, after, afterwards, again, against, so on and so forth. You see whole words here, right? Not stems. So again and against. Well, I guess it's not the same stem, but against, fairly close. You see it has the full word, not the lemmatized word, which is why we include it here. Now down below in this call, let's break it down one at a time. So word tokenize is a function that will take our document and tokenize the words. Now what does that mean? Well, remember that a document is, a text message, a chat message, an email, or voice to text, or in our case, it's a job description. So we're going to take that and we're going to tokenize the words, which means instead of having one long sentence, we'll break it up into a list of individual words. So iterate over that list of individual words. Okay? Now, if the word is an alphabetic word, then we want to consider it. And if the word is not in stop words, then we want to consider it. Both of these need to be true for us to consider the word. So is it alphabetic? And is it not in stop words? So the not in stop words is effectively filtering out any of these words down here from the document that we're tokenizing up here. What's going to remain then are only the words that are not in stop words and only the words that are alphabetical. And this will give us a much more concise list. So now let's go back down to our CountVectorizer. And notice that because we're filtering out those stop words, we no longer need that stop words equals English that we had before. Let's run this again and see how many words we get. Notice now we've reduced our data set to 183 rows. So remember, we started with 267, then stopwords took us down to 227. Now by lemmatizing, we have reduced it to 183. So fairly significant order of magnitude compression in our data set. I want to take a look at all of the rows. Now, while I've had the video paused, I've been changing this display max rows to 100 or 1000, depending on if I want to see just a summary of the data as we see here with a few samples and then the total count, 183 rows, or if I want to see all of the data. This time I want to see all of the data, so I go ahead and bump that to 1000, and we'll run this one more time. And now take a look at the result that we have here. We have ABIL. What we don't have is the word A about, above, across, after, any of those. And if you rewind the video a little bit, you'll see before I did the lemmatizing and the stop words, we did have the word A in there. And it was obviously a very frequent word, so one that's not important in our analysis. So see, abil, accessori, you see these are all roots, right? So it's both filtered out the stop words and it's taken us down to the stem. Yeah, several good stems it looks like here. So we have high, we don't have high or highest, we just have the word high. I imagine manage, that's a big one, manager, management, several ones there. So we were able to reduce this data set fairly dramatically. Now, let's take a look at how we can do a TF-IDF transformation on the data. Fairly straightforward for us to do. And it will be a bit more meaningful at this point when we have taken all of our documents, but we've also been able to reduce them to make them a bit more efficient. So we simply construct our TF-IDF transformer. Remember, transformer assumes we've already done the CountVectorizer. Tfidfvectorizer will do that for us. But given that we wanted to switch a few dials here on both stemming and lemmatizing, or rather lemmatizing and stop words, it was best to use the transformer. Then we compute the frequency, and then we print the document matrix. So here we can see MANAG. That's a really good test case for us here because manager, managing, that would likely appear in a lot of jobs that match my profile because my profile title is engineering manager or a director of engineering, depending on what job you're looking at. And if we take a look here, we see 1.33513. That would indicate in several of these job postings, it has seen the word manage or manager or something that has that stem because a low number says, okay, I've seen this in several documents. But then we have a few documents that have a higher number, which indicate that manage is more frequent in those documents. That word is more frequent in those documents than it is in other documents. Let's take a look at a few others that we have. So knowledge, you see this one has 2 records with about 2.38. So that says, okay, across all these 8 documents, I saw this word 1 time in 2 documents. Or it could also be I saw it the same number of times in 2 documents. But nonetheless, we can see that. See if we can find a big outlier here, something with a very large number. Just doing a quick scan. Design. So this one's interesting. So design was found in 2 different job descriptions, but much more frequently in one job description than another. Now you notice that this data set is what we will call sparse because there are quite a few rows that have 0 or not a valuable number in them. Well, TF-IDF itself gives us a sparse matrix. And that's a little way to compress a matrix that has a lot of zeros or empties in it. What a sparse matrix does is it basically takes the zeros out and says, I don't care about them. And instead of showing them in a 2x2 frame like this, it will say, okay, at this location, there is this number. At this location, there's this number. We can use that to reinflate a full matrix and then simply fill in the gaps with 0. Now, remember that we start counting with 0 in Python. So when you see 0, 175, what that means is document 0, or the very first document, and word 175, which is the 176th word in that matrix that we were looking at earlier. Okay, so remember, we have lots and lots of words here, or actually, let's take a look down here. Lots and lots of words here. So about 183 words here. And if I do the math right, okay, 0175 would put us right about here. So you see, sure enough, it's saying in column 0 and in row number 175, you'll find the number 1980829 and change. And sure enough, that's what we find here. In document 0, word number 169, we'll find the number 2386294. And sure enough, we see that here. So this is simply a way to compress what we see up above. Now it's time to start thinking about how we can use our data set for some predictive modeling. So first of all, we have our sparse matrix, but we need to get that in a form that's a little bit better for supervised or unsupervised learning. We can use something called truncated SVD, which uses a bit of linear algebra to compress the data set and also pick the top features out of all the features we have. We still have 183 features, which are all of those words. So truncated SVD, we can give it a parameter saying the number of features. It compresses the data and then says, okay, these are the ones that I'll give you to use. I did a deep dive in this to say, okay, what's it actually doing under the covers? And what I found, number one, was very little information on the internet. And number two, what I did find was a whole lot of linear algebra. And at that point, I said, okay, that's probably over and above what we need to consider. So don't worry about the details, but that's effectively what's going to come next. Luckily, the implementation is a lot easier. We just have to get this truncated SVD, tell it the number of features we want to use, normalize the data, make a pipeline, and then we can transform the data. The output looks like this. What you'll see is it's a list of lists, and each of our documents has its own row in that list with numbers that represent the features for that document. Once we have that, we can move on to some type of regression. I pasted a sample in here, but I didn't actually run it. Reason being, I don't have a good number of documents indexed for this yet. So for 20 features, or however many features we use, so far I only have 8 job descriptions. I could probably continue and add more in there, but that would naturally take a bit of time to get the amount of data that we need. So let's think about some business cases that we could use here. One is, naturally, match candidates to jobs. I'll tell you, at the moment I'm recording this video, the job, the unemployment rate in information technology, which always seems disconnected with the rest of the economy, is a bit disconnected. And the unofficial proxy for that is how many unsolicited emails do you get on LinkedIn telling you about a job. And I don't know about you, I have not gotten many in the last couple of years. And as a matter of fact, I know when there's a job open, there are a lot of people who apply to it. Sometimes that's reversed. Sometimes you have a job opening and few people apply in a different economy. But where we are right now with layoffs happening and all, you can end up the first day you release a job with 100 applicants. And naturally, you don't have time to look through every single resume and find the best match. And that's where I will tell you what you'll hear a lot. Be brief in your resume, be concise. Don't do an 8-pager. Typically, that matching process is a very quick look at a resume, maybe just a few lines on it, and look at the job, unless it's automated like this. So with multiple variables, what would be really neat would be to do a k-means analysis on this. In other words, instead of having job descriptions as our documents, make resumes the documents, and then add the job into that collection, and then do some k-means clustering. Adjust the number of clusters, and then find the cluster where that job falls, and look at the resumes that fell in that same cluster, and boom, at that point you've automated the process of saying, of the 100 resumes that I've received, these are the ones that are the best match, and they're the ones I'm going to focus on first. On the other hand, we could use what I've put together where we have job descriptions and maybe one resume, and we could say, okay, how does my resume stack up? If I look at job descriptions where there's a low TF-IDF number, that means, this is something that is maybe a good fit, but not a unique fit. On the other hand, if I see a high TF-IDF number on my resume for a specific word and a high TF-IDF number on a specific job, we can say, okay, it looks like we might have a unicorn here. We might have a case where this job is looking for specific skills that are common in my resume, but maybe not so common in other jobs. Now, another thing that we could look at that would be equally interesting is mining data for job salaries. So you'll notice that some, but not all jobs will post a salary here. And what would be interesting with that is say, okay, these are keywords that lead to this salary, or these are keywords that lead to that salary. That's a really good look at linear regression to say, okay, if we look at the highest paying jobs, what are the skills that they're looking for? And then we could kind of reverse engineer that into here are the highest paying skills. Okay. What can we do with that information? Quite a lot, actually. We could take a look at what skills maybe a college student would want to have upon graduation to land a really good job. Well, on the same note, the college needs to look at what skills are we offering, and are these skills that will lead to a good job out of college? Another thing that would be interesting, think about project management. What if we could grab text data and prices and have a look at inflation? One of the biggest risks that we'll have in a project is cost, right? And if we have a period like we have had in the last few years where inflation is, number one, higher than normal, but also less predictable than normal, this could give us a bit of intelligence to say, okay, we need to rethink our project cost because of this factor. So let's go back and reset expectations. So for matching resumes to jobs, I've come out to LinkedIn. I grab my About, which I will confess I have not updated in a good while. Some of these things you really just don't hear much about anymore. WebSphere, maybe a little bit, not so much. Hibernate, a little bit, not so much. But also I have a very scattered About talking about horticulture, MBA. You know what? This is a lesson to me. I think that should I enter the job market again, I need to tweak my About. And maybe what I should do is I should go ahead and look at some of these job postings, look at the frequent and infrequent words, and tune my profile to be a bit of a better match for that. But nonetheless, I added this to a new text document called brandon.txt. I went ahead and reran this part where I'm reading in all the documents, including brandon.txt. And sure enough, towards the bottom, experienced manager, architect, programmer, trainer, and professor with a demonstrated history. And then our corpus, you see that I am now the additional member of the corpus. So once again, this is ideal for something like k-means, where we might want to take a look at what jobs my resume is closest to. I reran the TF-IDF with myself as document number S9 here. And even starting with the CountVectorizer, you can see where there are certain jobs where I may be a match, like account. My undergraduate degree is in accounting. So that could be accounting, or that could be just accountable for. In this case, it's probably accountable for. So we want to be careful there, because account, could have a couple different meanings. But we keep scanning down. I can assure you that you'll find manager in my overview, and you'll find that in several other job descriptions as well. So manage, you'll see all but one job description. One has it 5 times. My resume has it 1 time. Message, looks like my resume is the only one with that. But nonetheless, we can keep going down, and I did do a TF-IDF. Now, it's a little tricky here because as the 9th document, mine kind of word wraps a little bit, but nonetheless, we can still get an idea of some things. So you see account, I have a 2.5, so a relatively high number, higher than 1, but not the highest number. And that indicates that this word was found in a job description. Now, curiously, 3.1972, that's a high number, and that indicates the word was only found in my resume and not in any of the job descriptions. So these are ones we might want to rule out. As a matter of fact, perhaps we could do a filter and say, okay, only show me jobs and only show me words where there's a union. So only show me where my resume has a word that you would also find in a job description. Let's keep going down, look for some other numbers. We see background, yeah, that's in 2 different jobs. BUSI, probably business. That's in several different job descriptions. Once in my resume, but it looks like twice or so in this other description. Keep going, look for anything else we can see. EDUC, so that has a very high number. You see that it's not in any other words, and I suspect the higher number there is indicating that it is not a word that's found frequently in our corpus at all, and it's unique to my resume. So an uncommon word that is unique to my resume. 2.096, so industry, we see that that comes up in a couple other job descriptions. Again, we can look at this visibly. We could also, if we want to go ahead and do a cluster on it, I know I covered clustering in a separate video, and this video is getting a bit long, so won't actually walk through that, but that's something you could obviously do as a next step. Now, the other case I gave is looking at this data to try to predict job pay, because we know that some jobs have that pay listed, others do not. So for that, I'm going to go back and remove my resume here, and I'll add a second argument to our read file function. So maybe we'll say file name and then pay, something like that, or that's effectively our target. Now, up where I'm defining corpus, I could also define pay as a collection. So these 2 collections should have the same value. Now, in my function here, I will simply append whatever pay is passed in to this pay list. So pay, append, pay. Now, I'm going to have this target that has 1 value for every document that I'm processing. The value here is, if I run down to my linear regression, that effectively becomes my Y value. So here where I have the train test split, I start with the TF-IDF matrix. Now this is after having normalized it, compressed it, and doing all that. And then I simply pass in pay as the second parameter to say, okay, these are the features, and this is the target that we're trying to predict. And then we do our regression model and we score it. Now, as I mentioned, I don't have a large body of documents here. I don't have a large corpus, so I'm not going to go ahead and do the regression because it would probably result in something meaningless. But this actually would be fairly easy to automate. I don't know if easy is the word, but definitely possible. If you think about having some kind of bot that could go out and scrape LinkedIn, grab the job descriptions, but then also look for the pay as a keyword, boom, boom. Okay, there you go. We could put those 2 items into a document. We could have pay, and then we could have the job description, and then we could have a Python script run through, separate out the pay, put that into our pay collection, and then separate out the document, put that into our corpus. And if we ran this across a big enough series of jobs, we would have a big enough corpus, hopefully, to be able to look at the significance of certain keywords on pay. That would even be like an exploratory model because we could look at the coefficients behind each keyword. So that's a good next step for this. As I say, this video is just looking at preparing ourselves for that. So I'll leave all of that as an exercise to you. But nonetheless, I hope you found this video helpful, and I look forward to reading your comments. Thank you.